All right, in this example, we are actually going to find the center of mass of a laminate. So now we are going to find the center of mass of a semicircular plate with radius r. Now, semicircular means half of a circle, so we're looking at just half of a circle trying to find where the center of mass is there. In order to set this up, I need to give it a coordinate system. So I'm going to write the semicircular area as the area under a function. Specifically, there we go. Here's our xy plane. The semicircle here is going to be y equals the square root of r squared minus x squared. So that this distance right here is r, this value right here is r, this value right here is negative r. Okay, and I'm going to try to find the center of mass of this shape. Now, one thing that I can tell already just by looking at this is that the center of mass is going to lie somewhere on the y-axis. You can tell that because the left side and the right side are perfect mirror images, right? See the beautiful drawing where they're perfect mirror images. Now, imagine an actual semicircle, right? If the left and the right parts were truly mirror images of each other, we would have that nice balance where all of the mass on one side balances all of the mass on the other side. The centroid here is definitely going to be on the y-axis. The question is, how high up? It's got to be somewhere in the middle here, but we don't know exactly where. So what we're really interested in is y bar, the y coordinate of the centroid here. We're pretty sure just by looking at this that x bar is equal to 0. So how about y bar? Well, in order to find y bar, we are going to take two integrals and divide them. We're going to have the integral of 1/2 times f of x, the quantity squared, and we're going to do that all the way from negative r to positive r. And then we're going to take that's the moment value there, and we're going to divide it by the mass value in order to find the centroid. That's going to be the area of the actual semicircle, from negative r to positive r of just f of x dx. Now we can also shortcut and figure out the denominator part of this relatively simply. The denominator part of this here is just the actual area of a semicircle, and that can be found using a geometry formula. We know that the total area of a circle is pi r squared, so the area of our semicircle here must be 1/2 pi r squared. So this expression is now going to become the integral from negative r to r of 1/2 times our function here, the square root of r squared minus x squared, the quantity squared, dx, all divided by 1/2 pi r squared. Okay, a few nice things are happening here. For one thing, we have a 1/2 in the numerator and a 1/2 in the denominator that can completely go away. The other nice thing is that the integral in the numerator is symmetric. We are going from negative r to positive r, and this expression right here is an even function. So instead of actually calculating this directly, we can replace this with the integral from 0 to r if we would like, to make it a little bit simpler for us. So y bar here is now given by the 2 times the integral from 0 to r of the square root squared is going to cancel each other out, r squared minus x squared dx, divided by pi r squared in the denominator there. Okay, so now actually taking the integral, r squared is just a constant in this case. So when we take the integral here, we're going to get r squared x. Then the integral of negative x squared will be negative x cubed over 3. So we are going to get 2 times r squared x minus x cubed over 3, evaluated between 0 and r, all divided by pi r squared. Okay, if we actually plug in 0 here, x will be 0 in both of these cases, and the whole thing will be equal to 0. So the only one we actually have to check is when x is equal to r. So we're going to have r squared times r minus r cubed over 3. That's going to be 2/3 r cubed in the numerator there. So we are going to now have 2 times 2/3 r cubed, all divided by pi r squared. So now to finish this problem, the only thing left is to simplify. We have an r cubed in the numerator, r squared in the denominator, so there's going to be some canceling there. 2 times 2/3 will be 4/3, so we end up with 4 pi in the numerator, or sorry, 4r in the numerator, and in the denominator, just pi times 3, so 3 pi. So there we go. That is the y coordinate of the centroid here. So the y coordinate will be at 4r divided by 3 pi. Okay, so let's figure out approximately where this is. 4 over 3 pi is being multiplied by the radius. So 4 divided by 3 pi comes out to about 0.42. So we're going about 0.42 of the way to r here, meaning we end up right about there. That value is about 0.42 r. So if you go about 42% of the way up, from 0 to r, 42% of the way, that will be your centroid. And this makes a lot of sense because most of the mass here is down at the bottom, and the top is relatively narrow by comparison. So you'd think that the centroid would be lower down. So this matches up to our intuition here. Okay, so there we go. We've calculated the center of mass in a relatively straightforward context. We had a nice shape that we could take advantage of the symmetry of. In the next example, we're going to do one where we can't use symmetry.